welcome again to the lecture, just for the recording. What did we do last week? Or who can tell me what we did last week? It works somehow. Good. Yeah? Mm-hmm. 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 Okay. So we talked about how particles move. We talk about the sand falling down, right? We made some calculations about this. So how do particles move? We also talked about this in, detail?
We speak about the main transport mechanism of the aerosol, which is convection. And we formulate it with the Navier-Stokes formula and simplified it as much as possible.
Very good, but I don't agree to 100%. So everything you said is correct, but what was the relation of Navier-Stokes equation to convection? Was Navier-Stokes equation describing the convection? Yeah?
What are the forces responsible for the movement of the particle?
Exactly. So it's about which forces, it's like a force balance, right? And sums up the forces which are important for the movement of the particles. And convection was how in the Navier-Stokes equation? I don't want to know the equation, but how was the Navier-Stokes equation built off? Or built up? Built up, built off, built up. Yeah?
Analyzing the forces that are being applied on the particle.
Exactly. Do you remember them?
There is gravity force.
But was gravity force as gravity force in the Navier-Stokes equation? How was it shown in the Navier-Stokes equation? That's the direction. That's another thing. That's correct. Very good. But how was generally the Navier? I will for sure ask you this in the exam. Okay, for sure I will ask you this in the exam. But that's not how the Navier-Stokes equation is built up. How is it built up generally? How did we head it here? Yeah.
We had it in terms of convection, diffusion.
Okay, convection we already had, but generally, how was it? Like, try to do it methodic. Yeah? Very good. So how many terms are in the equation? 4, right? So try to make it quite simple. When I asked you this question, first say, okay, there's the Navier-Stokes equation. The Navier-Stokes equation consists out of 4 terms. What are these 4 terms? And then you said transient, convection, diffusion, and external forces. Why external forces? Or what is the idea of external forces? What is in external forces in this part? Why that part is not named gravity? Yeah? No. So I like the idea, but where does the drag force coming from? Yeah? Yeah, why? Because drag force is due to, and that's also something you should, when you learn this or try to understand this, what is convection, roughly? What happens in convection? Yeah?
Transport of material between
Mm-hmm.
density.
Mm-hmm. But this we also have in transient, right? What happens roughly in convection, yeah?
It's the transportation of the fluid.
Yeah, so not only transportation, maybe you can use another word, it's correct, but it's what the movement, exactly. So the fluid moves. The air moves and takes the sand with it, and the drag force comes from the moving fluid, right, around the particle. This is why we get drag force. So drag force is not an external force, and that's important to understand. Just because you have convection and transient, and then you look at drag force, and you don't find the name drag force in convection, you don't find the name drag force in transient, it doesn't mean that drag force automatically is an external force, okay? Always think about what happens, okay? The drag force comes from the movement of the fluid around the particle, which carries the particle away, and then we will have a drag also. And that's also so important. What is external forces? Or why is gravity an external forces? Which other forces could be external forces? Mm-hmm. Why?
Because it can also exert some force on the particle.
Again, sorry?
It can also exert some force on the particle.
Yes, but drag force can this also. So why? What is behind external forces? Yeah?
Because aerosol, by definition, should be stable, and
Mhm.
for stability, we need the force balance.
Mm-hmm.
So we should draw all forces on the particle and somehow analyze them
Mm-hmm.
to describe the movement.
Okay, that's everything correct, but it's not an answer to the question what is external force or why gravity is an external force. It's correct what you're saying.
Because the source of force is not in fluid and in touch with particle.
Yeah.
So
So
the system.
it's a force field. Okay, so you have a force field, and this force field goes to the particle. And this happens with electrostatic. If you have a charged particle, the field lines of the electrostatic will interact with the particle. And this happens in gravity, because gravity is a field, right, around the Earth, and this will be interacting with the particles. What is buoyancy? Where is buoyancy? Yeah? Mm-hmm. The buoyancy is related to the gravitational force. Okay, so if I have a body here, the air wants to go into this volume, right? So this one is, if I move it here, it pushes all the air molecules away in this area. Or here are air molecules, now there cannot be air molecules. So they want to go back. But they don't want to go back from each side with the same pressure. How strong they want to go back depends on the gravity. Okay, so if I don't have any gravity, there will not be any buoyancy. And since gravity goes in this direction, the pressure from here is much, much more, because we are closer to the Earth than from here. Okay, this is buoyancy, and this is why buoyancy is an external force. So for me, it's important that you not only can name these 4 parts, but I also want that you can explain me this, that you can name, okay, it's 4 parts, this is diffusion, external force, convection, transient, and for sure I will ask you, I can promise already, I will ask you exactly these questions in the exam, okay? So, because there I can really see if you understand this, if you learned this, if you invest time in this, or if you just looked at the slide and can tell me something about the slide. Any questions to this? Good. So did we calculate with the Navier-Stokes equation last week? Yes or not?
Like we derived from it, and we just
Again?
like we derived from it, like
How did we do this? Yeah.
We, in our case, we study with and then we neglect two terms and then neglect.
Okay, we neglect something. Okay, what did we neglect for the sand falling down? The diffusion. There is no diffusion, right? And what else?
I think we also transient.
Yeah, why transient? Yeah, was this the explanation for transient? Why we neglected the transient, or why the transient went off? Yeah? Yeah, so what was the model we are looking at? A sphere of beam, try to be more precise, it's correct, but it's important here. Yeah, aerosols, yeah, of course. I hope we're in the class. No, but what case did we look when we made the calculation? It's the same as with the Navier-Stokes equation, and also in other lectures we will have it. Always try to describe the model. Okay, we always work with a model. And what was the model we looked at to ask the question of the sand falling down? Yeah? Mm-hmm. Exactly. So we kicked 2 dimensions out. So we only looked at what was the model looking at. This comes basically from the model. Okay, try to set up the model you're investigating. So I ask you the question: how much time does the sand takes to fall down? And you don't answer this question directly, right? And you don't start with the equation directly. We did something else. We set up a model. And how does the model look like? Yeah? A ball, but this is already important. What does it mean when I look at a ball? A sphere, and what does it mean? This is really important to take away, okay? So I showed you the image from the dust over the desert, right? But now you say we look at a ball. Is this the same? Or what is the difference? Yeah? Exactly. We look at one particle. Okay, that's really important. So the first thing you say, okay, there's so many billions of sand particles, but I look at one particle. This is what I'm looking at, one particle. And now you come, what did we do with this one particle? Yeah. Exactly. We look at the forces which are working on this one sphere. And this could be different if we have billions of particles, because with one particle we neglect that they somehow interact with each other, okay? There will be Ricard-Sacchi equation and these things. This is for that's a different system. It's a different model we are looking at, okay? And this is also something I really want you, also this for sure I will ask you in the exam, because we see that students often have problems with setting up a model. Good. So we have a spherical particle and we have forces acting on them. So now it comes, in which directions do the forces act? Yeah? Yeah. Yeah. And gravity is? Yeah. Always? Okay, good. Buoyancy is always upwards, and what else? And the drag is in which direction? Always? No. In which direction is it? Yeah? Exactly. Yeah, so contradicting to the movement direction is the drag force. And from this, we directly can kick off some parts from the Navier-Stokes equation, because the gravity goes downwards, buoyancy goes upwards. What does it mean for the dimensions? Yeah? Yeah, very good. Only one dimension. So this comes from the model. Okay, try to make it in these ways, and then it goes easier. And with the forces, we already can kick out other parts, right? So the model, one particle, no transient. What can we kick out when we look at these three forces? What automatically goes out from our equation? Yeah? Diffusion, right? And then we just have to figure out, and since we need it later, I would like to know what is the equation for drag force in Stokes regime. We will need this later. This is why I would like to. What is the equation Stokes? Yeah.
3 delta
D or D square?
d squared.
Yeah? D or D square? D, okay. What else? Velocity, okay. D or D square?
dp square.
Mm-hmm.
The diameter of the particle is
Mm-hmm. Where does this equation comes from? This is a special case, okay? Do you remember what is in the basic drag force equation? What is in the basic drag force equation? Drag coefficient? Reynolds number? What else? Density? Velocity? Diameter of particle. Divided by 4, but what happens with the diameter of the particle? How is it in the general equation in there? There is it square, right? So the diameter of the particle is square, the velocity is square, but we have CD as a function of Reynolds. And for Stokes, we have 24 Reynolds. So we put in 24 Reynolds, and in Reynolds we have the velocity, and we have D, and in the other equation we have velocity square, D square, and here we have 1V and 1D, so both kicks out. Okay? So we have D and V. And there is a common simplification of this equation. And this is the drag coefficient, okay? Small f. And then this equation is very simple, okay? So we have a variable and we have a drag coefficient. That's it. Very simple equation. We will need this later. This is why I would like to introduce it here. Good. Did anybody of you make the calculation with the volcano? Yeah? And? Yeah? Very good. Okay. Did I gave you already the solution last week? No? Okay, 3.2 micrometer. Okay, so 3 micrometer is really good. Can you repeat the question? Yeah. Just for the others.
The question was to calculate the size of the project volcano during
Mhm.
the 15 months time
Mhm.
over 32.
Mhm. Exactly. So there was a volcano, and the particles coming out of the volcano went 32 kilometers in the air, and then 15 months it takes to settle down, and you should calculate the size of these particles, and it's around 3 micron. So we get a quite good idea, 15 months for a 3 micron particle. Good. Today I would like work more with this equation. And I want to finish this set of slides and then go into the next slide. And here I would like to talk about another term. So for the particle falling down, we have drag force, we have gravity, we have convection. And now I would like to look at diffusion. And this is quite interesting, related to this paper from 1827, right? 1827 here, on the particles contained in the pollen and plants, of plants, sorry. It's from Robert Brown. Who knows who's Robert Brown? Anybody of you have ever heard about Robert Brown? Yes, no? No? Yeah?
Yes, he is the one. It's called Brown's molecular movement.
Exactly, very good. And we will figure out why. So he's a biologist. And as a biologist, you can see he's interested in pollen and plants and all these things. In 1827, he was putting pollen from plants into liquid, into water, and then he was looking with a microscope at it. And then he saw them moving around. And this is what he's describing in his paper. And then you see here, while examining the form of these particles immersed in water, I observed many of them very evidently in motion. Their motion consisting not only of a change of place in the fluid, manifested by alteration in their relative position, but also not unfrequently of a change of form. So what he was saying there, he's seeing something, he called it particles, and we have to be very careful because in his paper he uses the terms particles and he uses the terms molecules, but not as we do it today. Okay, so he didn't know much about molecules. He just looked at a different variety of particles, and the big one he called particles, and the smaller one, because he looked at different sizes, he calls molecules. Okay, so it's not what we think about molecules today. He just looked at different sized pollen and dust and these things, and then he said the small ones, they move differently, so I call them molecules, and the big ones move a little bit slower, so these are particles. And he saw that they move around somehow and that they also change in shape. And this was a big question because also there was also the question about, okay, where is life from? What is life? Where is life sitting in an entity and all these things? So a big question. And basically there were two explanations, and the one explanation was, yeah, what you're looking at is alive. So of course it moves, because if I look at you, you will also move around, right? Because you're alive. And the second thing is that they say, okay, you have particle, or you have your pollen in water, and you look with a microscope, so you need a lamp. And the lamp creates heat, and heat creates in a liquid, what? Convection, exactly. And convection will go to the case that there will be movement inside. But Robert Brown was a quite tricky guy, and he kind of worked with these two questions. And the first one is he was also looking at dust. Dust is not alive, so he said, okay, but it moves in the same way, so it doesn't matter if what I'm looking at is alive or not, it moves in the same way. I see these kind of movements. And then he took an oil bath, and he not put a big cup of water, but he has an oil bath with droplets of water with particles in there. So there is kind of all the heat goes into the oil. So the problem of convection was also kicked out by the experimental setup. So, sorry, sometimes the experimental setup is quite important. So, and then he was saying both these kinds of particles, when immersed in water, are generally seen in vivid motion, but the apparent motion of the larger particles might in this case perhaps be caused by the rapid oscillation of the more numerous molecules. So what he's saying here is that he said, okay, I have big particles and I have smaller particles, and the small one kick the big one, okay? And funnily, he already called it molecules for the small ones, but this is not as molecules as we know it today, but he was very close to the real explanation with these sentences already. I don't know, no, he couldn't know, but basically he mainly gave already the explanation. So I would like to look a little bit more into diffusion. And diffusion we can explain quite simple. So if we make it generally, as you know from chemical classes, and all of you know what is diffusion basically. So we can apply this on particles. What is diffusion in general of molecules? How did you learn it in chemistry class or transport or kinetics or whatever? What is diffusion? Yeah?
Transportation of molecules due to concentration difference.
Yeah. So if we look at the Navier-Stokes equation, we look at the system without convection and without external force, and then we get exactly what you have, a concentration gradient and diffusion. And this is how you learned what is diffusion, right? So, and for particles, we can say, okay, they follow the same laws, so their diffusivity can be described by a single parameter, d, diffusion coefficient. And what we can do is to describe it, we will release a monodispersed cloud of particles as a sharp pulse. What does this mean? This is a model again to describe what is diffusion. So if I would ask you to draw a picture of the last sentence, okay, we do it like this. I give you 1 minute to draw a picture of the last sentence, okay? Everybody. Okay, I looked around a little bit and none of you made a correct solution, but that's really fine because it's a weird sentence. But the important thing is a lot of you tried to do something. Okay, that's the important part here. Try to model, make a model. Okay. And the model here is quite easy, but the fair point is it's maybe not so easy from the picture. And the idea is that we have, what is the meaning of monodisperse cloud? Yeah? Very good. All particles have the same diameter, the same size. So what can we say already about the model differently to the model we used for the sand? Already, can we say at this point? It's not size dependent. No, it could be size dependent, but we can describe the size very easy by one value. But still it could be depend on size, what we're looking at. Okay? The D would be constant, but it does not mean that diffusion does not depend on size. Okay? It's just easy to calculate because we have one size for calculating. Okay? So in this case, I agree that so the effect is size dependent, but we don't have the problem that size is a variable. Okay, good. What else? What can we say compared to the model? Yeah?
We are considering there an average for the entire.
Mm-hmm.
Here we can consider common velocity actually.
Mm-hmm. Yes, we can look at an average velocity. Okay, similar as we do it with size. So, what else? Yeah. Think about the model. How do we start with the model for the sand? And what changes now? How do we start with the model for the sand? Yeah, and here? Yeah?
Here we have the set of particles.
Yeah. If we would have one particle, we don't need monodisperse because we have one. And this one can only have one size. But now we're talking about all have the same size, so it means we look at a lot of particles. What does it say for the Navier-Stokes equation? We look at a lot of particles now.
Transients get adds up.
Yeah. So transient we cannot just kick out now, right? So because we can have a concentration gradient, we look at a lot of particles. All of them have the same size. Where are they? It's the last two words. Yeah? Yeah, sharp pulse. We don't need a tube. Tube we will have next week, okay? That's more complicated then. No. No tube. Where are they? Sharp pulse. What is the meaning of? They are all at the same position. Okay. So what we are looking at is a system actually this is not monodisperse. It should be monodisperse. So we have particles, we have a lot of particles, and a sharp pulse means they are all at the same position. In my drawing, they are not all at the same position because they are above each other. So what can we say about the dimension of my system here? How many dimensions do we have? Yeah?
They are eliminating x dimension. They are in one value of x.
Yeah, exactly. So all of them are in position 0. And this means we just have one dimension. All of them, the others we don't consider. And so how can they move differently to the sand particles? They can move now. Yeah? In one direction, one dimension, one direction? Or is it the same, one direction, one dimension?
One dimension.
Yeah, one dimension, two directions. And the two directions here is to the right or to the left. So how do they move? And how they move is depending on their single parameter d, diffusion coefficient. The chance to go left or right. On what does the chance depends here in this model? Yeah? Yeah, 50-50. There is nothing acting on them. So I can flip a coin for each particle if it moves to the left or if it moves to the right. And if the diffusion coefficient is very high, the particle will move directly a lot of distance. So what I need is time steps, right? And in each time step, the particle has to make a decision if it goes again to the left or again to the right. The time step could be anything, or we just keep it simple and say 1 second. Okay, so then it's easier to imagine. So after 1 second, each particle has to decide if it goes to the left or if it goes to the right. And each particle has a 50-50 second, and we do this for 1 second, for 2 seconds, 3, 4, 5, 6, and so on. Okay? So does this mean once this particle goes to the left, it will always go to the left? No. Why not? Yeah, it can always go left and right and left and right. And high diffusion coefficient means a lot. Low diffusion coefficient means a little bit. And here is it seen. So, and we very simply can describe this case by Fick's second law. And all of you know Fick's second law. And Fick's second law means n, or dn divided by dt. What is n here, probably? N is? No, we don't really work with mole of particles. The number of particles, okay? So I can count 2, 4, 6, the number of particles. And t is the time step, d is the diffusion coefficient, and x is the position. So I can describe the diffusion of particles in one dimension, so how they will move, the relation of distance over time by Fick's second law. This is what you know from diffusion. Can I directly solve this equation as it is here? No? Why? What do I need?
Because here we have second,
Mm-hmm.
here we have single.
Mm-hmm.
We have to equalize.
Yeah, what do you have generally to solve the differential equation? What do we need to... Boundary conditions. Okay, we need boundary conditions to to solve this equation. Here are the boundary conditions. The question is, what is the meaning of the boundary conditions? What is the meaning of the first boundary condition? I mean, I can give them to you and say, here's boundary condition, this is the solution, but tell me what is the meaning of the boundary condition? The first, where is the laser pointer? Yeah? Exactly. So how do you know initial state? From which point do you see it? Yeah. So, yeah, very good. T equals 0 is the initial state. So at the beginning, all particles, n, all are here. Okay. At the beginning, all our particles are here. That's the initial condition. And then we have two other conditions. What is the second condition? The meaning of the second condition? What do we can learn from the second condition? Yeah?
When the time starts, particles can be anywhere, either on the right or
Yeah, I don't read this from this boundary condition. I read something else out there. Yeah, that's correct. So if we go to infinity, there will be no particles there, okay? So they can travel, but the chance to go farther goes less. So in infinity, we will not have any particles. And what is the third boundary condition, yeah?
There is no balance set, so there is no movement anymore. There is movement, but there is no concentration. So it's at a given point now. At least for the starting point.
Yeah, for the starting point. And there it's correct, but what do we have at the starting point? You can learn it from first semester math. There you learn what is the meaning of this one.
It's going in both direction and symmetry.
Yeah, symmetry condition, right? So we have a maximum there. I mean, we cannot tell that it's a maximum, but from what we see, we know it's a maximum, not a minimum. And it means half of them will go to the left, half of them will by chance go to the right. So the derivation is 0, and this means we have a maximum, and this means symmetry condition. If I have symmetry condition, what do you think if I would make not 6, I would make 1,000,000? How would the distribution look like? You have now, with the boundary conditions, I ask you to make the graph which describes the movement. How would the graph look like? Yeah. So it would look like a Gaussian curve, right? So this is what we expect. I don't tell you really surprises here. And this is also the solution, and feel free to make the solution. So it's well known from literature that this will be the solution with given boundary conditions for x and t. And what you see there is the Gaussian curve, right? So the equation you should know, and I'm always happy if a student tries to solve it. Wait, I lost my camera. Ah, there it is. Okay, let's hope. Ooh. Okay, it works. So this equation is a little bit complicated, and it has a problem. If I ask you in one dimension, what is the mean distance a particle travels by diffusion? What is the mean distance the particle travels? Yeah? 0. But this would mean we don't have diffusion. So whether we work with the full distribution, but the mean value is 0. So, and you said about mean velocity. So mean velocity is very good to describe, quite easy, the mean size and all these things. But if the mean diffusion is 0, we don't have diffusion, and this doesn't work. Does anybody has an idea how we can get rid mathematically of the minus part? Yeah? Yeah. We can square it. When we square it, they will not cancel out. If we square something, the minus will go away, and this is basically what you can do, and this is called the second moment of the spatial distribution. And the second moment is the same for the people who have particle technology with me. When we calculate one entity like mass into number concentration, then we also use moments to calculate from one distribution into another. So mathematically, it's the same, but for complete different reasons. So we take the second moment to make the square. And the nice thing is that the solution of this is an extremely simple equation. And this equation depends on just two variables. So if I want to understand in one dimension, what is the diffusion of my particles? I just need to know their diffusion coefficient and the time. That's it. Okay? Does anybody of you knows the name of this equation? Any ideas? Yeah? Yeah, make a guess. No, it's named after two scientists.
I would have guessed now Braun's.
No, no, not Brown's equation. Even better, but we will see. Okay, so if I, just to recap, so if you want to describe the diffusion of particles in one dimension, this is, voila, how you do it. Very simple. You can derive it from Fick's law. Okay, then you would make a little bit math and you would get it, but you can also put this into a Python code, or in this case it was done in MATLAB, but no, I think it's also Python code. So, and this is what you see here in this GIF. So you basically see exactly this experiment with now 1,000 particles. And in the last step, so you see how they diffuse, and the computer, it's very easy for the computer to make these time step left, right, left, right, left, right. And in the last step, we just order them. So what happens then is that you just order, okay, how many go a little bit, how many go a little, tuck, 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 tuck. And then the red line is not the solution of the equation. The red line is the fit of the results. And this is a Gaussian distribution. So it's a very simple case here, but it's a very nice example how you can connect math to experiment or to simulation in this case, okay? Because we are simulating left, right, and what we're getting is a Gaussian distribution. We make a model where we say we can describe this by Fick's second law. We solve the equation, we get a Gaussian distribution. Very good fit of these things. Good. It's theoretically quite nice, probably. I don't know if it's nice for you. For me, it's nice to do these things. But what can we do with it? So far, I told you how particles move. And I told you Navier-Stokes equation, and you should understand a little bit the Navier-Stokes equation. And now we have discussed all four terms. I showed you with the sand, I showed you a very simple one-dimensional example of how one particle can move by convection and by external force. And now I showed you a very simple example in one dimension, how particles move by diffusion, and these are just theoretical cases, simple examples, and so on. But if you merge all of this into a three-dimensional case, we cannot solve it that easily, but then you can take a look at this one, and this was done during the Corona time, and then you see basically all these cases in the three-dimensional case. So you're sitting in a class, and you see that somebody is breathing. And we have convection due to temperature change and we have diffusion because the particles diffuse in this size scale. We have a three-dimensional case. So the computer is solving numerically the Navier-Stokes equation. And what you see is how droplets, which coming out of my mouth, are traveling through a room. Okay? Why it was 2-3 years ago interesting? Corona, correct, right? And this is nothing else than a more complicated solution of what I showed here. So we see diffusion there, we see thermal motion. Thermal motion is always important to cover longer distances. We see the settling, the gravity, drag, all of these things are in these computer models, okay? And the funny thing is, what you see is also, if we look again, you see that also the student or pupil or whatever, person sitting there, you see that he or she is breathing normally, but now you see also one other thing. Yeah. This is coughing, okay? That's what, and you see how it works. And the other thing is we directly can tell that this is probably good work because we have a natural feeling for this. What looks exactly the same? Exactly the same. If somebody sits in the room, what would he or she is doing? And this behavior would look exactly like this, yeah? Smoking. Why? Smoking is nothing else than breathing, only the concentration is higher. This is why we see it. Nothing else is different. Okay, the concentration is higher, and we know how it looks like when somebody's sitting in a room and smokes. This is what we know. So therefore we know that what we see in the simulation, and the simulation helps us to see in the concentration level where we don't see, but that we get a feeling like, that makes sense somehow. Yeah?
Does the temperature makes a difference to the movement of
Mm-hmm. Yeah, that's a very good question. Can anybody answer the question? Does the temperature makes a difference? Yeah? Yeah. So the nanopart or the particles in this size range, they diffuse a lot. Diffusion is high for them, but the main driver for longer distance travel, and we're talking here about longer distance in the full room, is convection. And convection depends on temperature. Okay, so if everything would have the same temperature, the room directly has completely the same temperature as we have, and nothing would move, we wouldn't have convection, and then the behavior would be completely different. Funnily, in the computer, you can do this very easy, right? You can set the temperature gradient to 0, and then you will see these things. So therefore, as I told you, this is the picture of my brother-in-law smoking, and all I told you about Navier-Stokes equation, we can again relate to smoking, right? So how these particles move, and this works quite well. Good, now I would like to come to another guy. What is the most famous scientist you know? Einstein. Tesla. Einstein. Einstein. Newton, very good. Okay, so it was 10 times Einstein, 1 times Tesla, 1 times Newton. Do you know what Einstein was the correct solution. Do you know what Einstein did in 1905? 1905. Do you have ever heard the term miracle year? Yeah, what is miracle year? Yeah, very good. But in relation, miracle year? Okay, anybody of you? Okay, so it's called, even there's a Latin term, it's called Annus Mirablus, 1905. Annus Mirablus is the year where Einstein made 4 publications and his PhD. So if you want to do a PhD, this is the benchmark. Okay. And all of these are quite different publications. And he made all of this, at least he published all of this in 1 year. Do you know one of these 4 papers? The content. I mean, it's in German because the basic, his English was not so good. And at this time he was living in Germany, so he published in German. But do you know topics of these 4? I don't need the titles, but do you know what he was publishing there?
General relativity.
Yeah. So in this case, it's special relativity, what he's in this year publishing. This is this one here, Elektrodynamik bewegter Körper. This is special, or the basics for special relativity is here. So basically, this year he published the basics for special relativity. What else? For what did he got a Nobel Prize? So in this year, photoelectric effect, okay, basic for quantum physics, and the paper with E equals mc square, the paper with the basic of special relativity, and the right paper is about, now you come, what is the right paper about? No, not convection. The other one, what you're telling all the time during the lecture. Yeah, the fully right paper. And at the beginning you talked about, I showed you already another paper, and then you made a very smart statement.
In the molecular movement.
Yeah. Look at the title. So this is basically related to Brown's work. Okay, he gave the answer to Brown's work from 1827. And the Nobel Prize he got for photoelectric, then E equals mc square, special relativity, and he solved the problem with the Brownian motions. He solved it, but to honor Brown, they called it Brownian motion. But he solved it with another guy. He solved it half a year earlier, but the credit mainly go to Einstein. And this is why this equation, x squared equals 2dt, is called Einstein-Smocholski equation. Okay, that's the Einstein-Smocholski equation. So it was quite a successful year for him. And I mean, you are not in this class for these things here. This is physics class, and I don't know much about it. But this one is related to what I showed you before, Navier-Stokes equation. And the question is, how did Einstein solve this problem? And he did it basically in the same way as we do it here in the class. So he sets up a force balance. And this is what he's doing in the paper. He's sitting there and makes a force balance. And in the force balance, you already see 2 terms you should recognize. What is the term in the middle? Drag force, right? So he's thinking about a model again. We're talking about models. So he's thinking about a model. And in the model he says, okay, I have one particle. And Brown tells me this particle is just moving around, somehow randomly. It's not falling like the sand. It's not diffusing like here. It's moving randomly. And when it's moving randomly, there should forces act on this particle, right? But now I have 2 dimensions. I don't consider up and down. It makes it very complicated. But it could go to the left and the right. It could go up and down in the area of the board. So it could go in this direction, this direction, this direction. So 2-dimensional case. And if it moves, it's in a fluid, there should be a drag force, okay, resisting from the fluid. And if it moves all the time in each kind of direction, there should be inertia, because it's accelerating somehow. And we need this. So far for the settling, we don't look at acceleration. But here, if we have a change in direction all the time, we have inertia. So this is inertia, right? M times A. And this is drag. And then he added something. And this is what also was described in the paper. And this is what he called fluctuating collisions. Okay, this is what Brown was also describing, that they also somehow collide like a bumper car or whatever. And this equation, I don't want to go through the full equation, but just to give you a little bit an idea. So drag we have here. And if you have these complicated equations, you want to solve them. Now you make use of this one, okay? This will be constant. You don't want to carry away with you all the time, right? So you simplify it. And then we have these fluctuating coalitions, F, T. And what he's doing is he's dividing by m, multiplying by x. And then this equation somehow rearrange. And then we have here this is what we call beta. And beta is mobility. Mobility is similar to electric mobility. Electric mobility is the mobility of a particle in an electric field, but we can have it also without electric, right? Mobility. Like, I don't know. If you look in terms of, I don't know, my favorite football team, there you have Süle, he has not high mobility, and you have Adeyemi, he has a very high mobility. You can think about these terms. I don't know, who knows these players? Okay, then at least for two people this works, okay? So high mobility means you are very flexible, you are very fast. Low mobility means you need your time, okay? And then we would have something like, here at this part, and here he also has another term, I think, I can look it from the slide. It's A as a function from t is ft divided by m. So we would have here x times ft. So we have somehow simplifications of the equation, okay? Why we are doing these simplifications? Why we are playing around with the variables here? Why we are doing it? Yeah? To simplify the equation. And why we want to simplify it? What is important when you want to solve differential equations? I mean, sometimes it's very easy. You make an integral and then you know how to do it, but it's not always this easy. And what are you doing? Like here, it's not that easy. And what are you doing with, here this is called mobility. And then we rearrange. What do you want to do normally? Yeah? In one term, yeah, we simplify it. That's really good, but we're doing this for purpose. We don't do it because it makes fun to rearrange equations. We don't do it for a purpose which is very important when it comes to differential equations. Yeah? We reduce, exactly, but why? What is important when you solve differential equations? Yeah? To separate the variables, right? Separate variables, integrate, but sometimes it's not that easy right away. And then it gets really a lot of math. That's correct, but basically what you do is you look for a recept. Okay, so a lot of equations are solved. So to don't do all the work alone, you just look for standard ways to solve an equation. Because sometimes the equation you cannot just integrate and there is the solution. And what is happening here, and this is a standard equation, okay? So if you have an equation where dv divided by dt, and then you have plus something, and then you have v squared plus something, okay, you will find recipes how to solve this equation. Doesn't matter if you look at drag, or if you look at statistics, or if you look at biology, it doesn't matter. This shape of equation will always be solved in the same way, okay? And this is why we rearrange it. This is why we don't keep it in this way, but we rearrange it so we bring it into the right position that it's easy to solve. And then you can just go after the recip, and then you go for integration. So if you integrate and reshape, then this will be the solution. And then you can rewrite. So rewrite means we have velocity times, or average velocity times average distance. And velocity can be written as dx divided by dt. Okay, so this is velocity here. And then we can put the x in here and we will get a 2. And then we can write this part here. Okay, and then we have again a differential equation. This can again be solved. And if this is solved, we will get this solution. And for this solution, the whole right term can kicked off for large T. Okay, so all this goes away. So at the end, we will have a very simple solution. X squared divided by 2 is roughly v squared divided by beta t. Okay, very simple solution. I don't want you, it takes time to do this really step by step. I just want to show you the way how to go through it. Okay, if you want, sit down at home, go through it time by time, but the important is that you understand what we are doing. So we have the force balance, we put in the forces, we rearrange a little bit to give it the correct shape, to make it solvable, then integrate, rearrange, integrate, we will get this. And then in the paper you will find something Einstein made, and this is, he made an assumption, and the assumption is that he says, okay, the kinetic energy he relates to the temperature of the system. He said, okay, there's a difference if I have a very cold or a very hot system, and this will be somehow related to the movement. And with this assumption, we will get a quite interesting solution. And the solution can tell us what is D, what is diffusion. Because so far, I didn't ask you what is diffusion. In the beginning, I asked you what is diffusion for molecules. But diffusion was just a coefficient. Right? Diffusion was just a coefficient going to the left or going to the right. That's it. But here we have now an expression, what is diffusion? And we know the Einstein-Smoluchowski equation, right? This is the equation from diffusion in one dimension. X squared divided by 2 times. So if this goes here, this goes here. No, if this goes here, we would have the old equation. But now, if you take a look here, right? So we can put this with another t in here. And then we can reshape it to this one. And from here, and Einstein's assumption, we can replace this one by kT. And this means we can relate the diffusion coefficient to the thermal energy of the of the system. And this is basically the explanation of diffusion for particles. And diffusion of particles works in the way that we have molecules, like real molecules, not the one Brown was telling about, and these molecules by chance will hit the particle. And we're talking about 10 nanometer, 100 nanometer. So these particles will see the molecules, and they will feel the molecules when they hit the surface. And if a lot of particles, molecules, we have to be very precise, would do this, what would my particle do then? Yeah? According to this picture, what would the particle do, probably? Yeah, it would move into this direction, right? And now, what happens now? And at the end, we would have something like, and this would be the movement of the particle, right? And this is what is called Brownian motion. And this is how particles diffuse. Particles diffuse because they are bombarded by molecules, as I am bombarded by molecules, but I don't feel it, I'm too tall. But these guys, they feel it. and this is how they move. And Einstein gave the solution for this problem. And to honor Brown, it was called Brownian motion. And here in a good. So here we are done with diffusion, but we made a quite interesting assumption. And this is that on the one hand side, I tell you very small particles and they somehow feel the molecules. And on the other hand, we use very simple equations for drag. Do you remember this regime we are in here? We talked about different size regimes. So this is a very oversimplification we are doing here. Yeah? Monodisperse is right, that's the size, but what I mean is basically that we have different regimes, and these regimes depend on the size of the body. So then we have different ways or models we use to describe what is happening when it comes to fluid dynamics, right? Drag is fluid dynamics, and fluid dynamics always work with a very simple, important assumption. Yeah, it is related to micrometer, but fluid dynamic also works with meter, with kilometer, right? But what do they assume that their equations work? Also this equation here. Yeah? Stokes regime, and this is related to another assumption. We had it in the first lecture, we had this table with all these different sizes and whatever. And then we had three regimes. For the big one, then something in the middle and small. Yeah? Yeah, I'm asking for it. Yeah? Laminar, this is related to the velocity, but not really to the size. I mean, it goes a little bit with size, of course. This is why we have Reynolds. But all these laminar, turbulent, all these having an assumption behind it to describe it.
Are you talking about force regime between the particles?
No, it's a more general assumption behind all of this, that my equations, that I can make simple equations describing what is happening. Yeah?
Free molecules, transient,
Yeah, very good. No. First, very good. So we have continuum, transient, and free molecular. And fluid dynamics normally works in continuum. And continuum means we don't care about what? What we don't consider in continuum. We don't care about it. That's the simplification. This is why we can calculate in large distances. Something I don't care at the moment here also. Yeah? Time? No, I care about time. So I know I still have 10 minutes. So I care about time. Size? Size is important according to this equation. With size, we are jumping into different regimes. This is size dependent, that's correct. But I don't neglect size in continuum. What do I neglect? Yeah. Or here not. 1, 2, 3, 4, 5, 6. You can do it for 1, you can do it for 1 million, you can do it for 5. If you look numbers in the Fick's second law, we had numbers as a variable. Atoms. I don't care about atoms. Okay. So in continuum regime, the simplification is there are no atoms, there are no molecules, there's water. That's it. Finished. It has a temperature, it has a density, but that's it. And this helps us to get these simple equations here. But if we go in a smaller size, Now we feel the atoms. It's really hard to neglect them if you feel them. And the problem is that in continuum, if this is the surface of a particle, and the particle moves through a fluid, I make a very basic assumption about the fluid flow on the surface. In laminar flow, how looks the fluid flow or movement close to the surface of the particle? All of you know this picture for sure. What is the velocity profile around the particle? Very close to the surface. So it's a very big particle in this case. How does the fluid move here? Directly on the surface. Yeah?
It's not laminar.
I would like to know it for laminar. For turbulent, it looks a little bit different, but I think the assumption is the same. What is the movement directly at the surface of the particle? Or the molecular movement. Basic assumption in fluid dynamics. Not random. Do you know it?
Yes.
Yeah?
When the particle moves this, on the surface goes.
So the particle moves in this direction, so the fluid moves in this direction. But how would the image look like at the boundary here? Okay. And this is an assumption in continuum theory. The first layer of molecules, which are not really molecules, they don't move. They have a velocity of 0. Okay, and then you have this velocity profile close to the, you know this picture, right? So, but if we go now in a size where we see the molecules, this doesn't work anymore because these molecules, they move. Okay, doesn't work. These two pictures don't work together. And this is why we have a transient, and we also have what we call free molecular regime. And this means this equation, which is based on this assumption, doesn't work. And to figure out in which regime we are, so which equations we can take, we have the so-called Knudsen number. And the Knudsen number is a very simple equation. As you see here, Knudsen number defines the ratio between the molecular mean free path, lambda, to a representative length scale. Representative length scale is always very easy, the same as in Reynolds number, it's the particle size, right? That's our length scale. And the mean free path is something we will see in a minute. So we divide 2 times the mean free path by the particle size. And this will give any Knudsen number. And if the Knudsen number is larger than 1, the mean free path of a molecule is comparable to the length scale of the problem. So this means if the Knudsen number is larger than 1, we are in free molecular regime. So continuum regime does not work anymore. If the particle is very large, it would mean the Knudsen number would get smaller, smaller, and smaller. If this goes high, this goes down. And if the Knudsen number is smaller than 1, roughly, we are in continuum regime, and then we can work with these equations. That's a little bit oversimplified. So what is the mean free path? The mean free path is the question if a molecule and another molecule, or the distance they have to travel till they collide, or till they meet each other. Okay, all the time molecules, here's like a firework at the moment, the molecules all the time bounce each other, we don't see it. And the mean distance they have to travel under standard condition is 66 nanometer. Okay, this would be for standard air. If we take 66 times 2, we have 132 divided by 100 nanometer, roughly 1. Okay, so this means at 100 nanometer, our Knudsen number will be already larger than 1. And this means continuum theory doesn't work anymore. So everything below 100 nanometer cannot be described by continuum theory. And now you see why we like to use continuum theory, because what you see here is the friction coefficient, and this is this F here. This is the friction coefficient, okay, drag coefficient, friction coefficient. And you see that the friction coefficient changes with particles diameter. And you see there is continuum theory here, dp, and then we have a transient, a slip correction, and then we have a free molecular theory, and the free molecular theory looks like this. So in the free molecular, if we are below 100 nanometer, and we want to calculate the drag force of a particle, remember the 100 nanometer drop, we use this equation. Basically, it's not a correct equation. Basically, we have to use this equation for drag force. But now you see the simplification here, right? Why it's so powerful, or why we like to do it. And there is also the slip correction. This is somewhere in between. And the slip correction is you take the normal equation here, and then you divide it by the so-called Cunningham correction. So this is a fit. You see here a fit correction. So if you're in the continuum theory and you want to calculate the drag force, this works. If you go a little bit below, you have to divide this one by the so-called Cunningham correction, so you adapt a little bit, and at one point this adaptation doesn't work anymore, and you need a complete new theory which describes the molecules as they are. Okay, with this, we are finishing this lecture, and I hope you understand why moving is so important. We really went intense into this topic, right? I took a little bit time. I hope it was not too, was it too slow? I can accelerate this. We can do this in 45 minutes. But I don't know if it's helpful to do this in 45 minutes. For whom it was too slow? Okay, you can let it me know in the evaluation. Okay, then I don't know. For whom it was okay to have it in this slow? Okay, so 3 people are 4, 5. Okay, yes. Okay, good. I hope after the last 2 lectures you know about force balances, Navier-Stokes equation, diffusion, convection, all these things. You know what I expect you in the oral exam. When I ask you how do particles move, what do you tell me? How do particles move?
Depending on the force.
Generally, how do particles move? Generally, how to describe this? How we can describe how particles move? Yeah, by the Navier-Stokes equation. And the Navier-Stokes equation has how many terms? 4, exactly. And now you can play around a little bit with these, right? So you can tell me what is diffusion, you know what is convection, you can give examples, you know how to kick out, you know how to make a model. And this is what I expect you from these last 2 lectures. I will upload the slide. Next week we will go even more into this stuff, and I will also show you some technical applications, because so far we have maybe some nice examples, we have some nice stories, we have a lot of science, but no technical, and next week we will make some technical examples, and with this we're done with the lecture. And I will see you later in the seminar. I will, after cutting, also say a few words to the seminar. And with this, thanks for the lecture, and see you next week.